The past few lectures have been about parameter estimation. How do we use our sample data in order to estimate a population parameter, like the mean? So we learned that we can take our sample mean and we can use it as a point estimate of the population mean. And we could even build a confidence interval around that estimate. And so this confidence interval would be where, say, 95% of the time, we would cover the true mean. But there's another way that we can look at our data. Instead of using our data to estimate a population parameter, we could instead guess a value of our population parameter and then ask ourselves, do we think our sample could have come from that particular population parameter? So instead of going from the data to the parameter, we could actually go vice versa. We could go from the parameter to the data. We call this new approach hypothesis testing. Now, we do hypothesis testing practically every day in real life. In fact, every time I go grocery shopping, I'm likely to do a hypothesis test. In fact, here's one time when my hypothesis test didn't quite go so well. Now, my family loves a particular type of almond milk. And I'm going to the store and I'm shopping for it one day, and it's the sweet vanilla kind. Okay. So I'm in the grocery store and I noticed there's a different brand of almond milk and it's on sale. I mean, it's like a good sale. It was $1 off. And so I'm thinking, okay, it's the sweet vanilla kind. It's just a different brand. It'll probably taste just as good. And it's $1 off. So we're fixing breakfast for our 3 boys the next day, and I take out this new brand of delicious almond milk. No big deal. They're young. What do they know about almond milk anyway? And it was $1 off. Well, to put it nicely, they hated it. I mean, their faces got contorted and nobody finished their cereal. And as you can imagine, I have never bought that brand again. So what was my hypothesis? Right? It was that this brand new almond milk is just as good as the old brand. And what do you think my sample data was? Well, that was my 3 sons' reaction to this new milk. And did my data support the hypothesis? Absolutely not. In fact, my data flat out rejected my hypothesis. So what is a hypothesis? Well, in general, a hypothesis is just an educated guess about something in the world around you. Maybe something that you can be able to test or experiment with or observe. Now, in hypothesis testing, what we really want to know is whether the characteristics of our sample match the underlying characteristics of our assumed population. So with the milk, my assumed population was that, it should be just as good as the old brand, right? The new brand is good as this old brand. But is sampling just 3 people sufficient? Now, at our breakfast table, the samples weren't even independent. Maybe one of them in the 3 were influential over the others. And it's not enough just to do a visual comparison, right? We need a quantitative way to evaluate our sample relative to some baseline. And that's what statistical hypothesis testing is going to do for us. Now, formally, a statistical hypothesis test is a claim about our population parameters. And when we do hypothesis testing, we're going to start with 2 pretty contradictory hypotheses. The first is our null hypothesis. We call that H naught. Now, this is the claim that's initially assumed to be true. It's like our prior belief, our old theory, the status quo, the current standard. And then there's the alternative hypothesis. We call that HA. This is our contradictory claim, the competing claim. Maybe it's the new theory or some alternative standard. And so we need a way to decide between the null hypothesis and the alternative. And this is what our decision principle is. We're going to reject the null hypothesis in favor of the alternative if our sample shows some strong evidence that that null hypothesis is false. Otherwise, we don't reject it. Statisticians also say we failed to reject H naught. like it's a failure if we can't reject the old theory. Now, hypothesis testing uses our sample data to make decisions about the population. We can specify our testing procedure with the following. So first, we're going to need a test statistic. Now, this is going to be some function of our sample data that we're going to use to make a decision, right? Whether or not we reject or fail to reject the null hypothesis. So that decision is going to be based on this test statistic that we calculate from our sample. Secondly, we need a rejection region. So this is going to be the set of all test statistic values for which the null hypothesis would be rejected. And then finally, we need a decision rule, right? So we're going to reject our null hypothesis if our test statistic falls in the rejection region. Now, the null hypothesis is assumed to be true, and we have to provide the statistical evidence needed to reject it, right, in favor of the alternative hypothesis. Now, if you've ever had jury duty or watched a court case on TV, then you've seen hypothesis testing in action. Seriously. So in criminal trials in the United States, the defendant is innocent until proven guilty. So in other words, our initial assumption is that the defendant is innocent. Now, let's see what hypothesis testing looks like for a population mean. In this case, the null hypothesis is that the mean of our sample is equal to the mean of the population. So mu is equal to mu naught. Now, this is assuming that the null hypothesis is true. Now, we often test whether our sample mean is different from 0. So H naught, that mu is equal to 0, would be our null hypothesis. The alternative would be that mu is not equal to 0. Here are a couple of examples of alternative hypotheses. We could test that our alternative is greater than mu naught, the mean under the null hypothesis, that is less than the mean under the null, or that is not equal to the mean under the null. Now, there are two types of errors that come up in hypothesis testing. The first is a type 1 error. In this case, we're going to reject the null hypothesis when it's actually true, right? We call this a false positive because we think we found something new, but we actually didn't. Another type of error that we make is a type 2 error. This is when we fail to reject the null hypothesis when it's actually false. We call that a false negative, right? Because now we've missed some new result. Now, we have two terms, alpha and beta. Alpha is going to be our probability of making that type 1 error. And beta we call the probability of making a type 2 error. Now, you can imagine we want to keep these as low as possible. But there's a contradiction, right? As soon as we try to balance the probability of making a type 1 error, well, it changes our probability of making a type 2 error, right? So we can decrease the rejection region and get a smaller alpha level, but a smaller alpha level is going to give us a larger beta, right? So our type 1 error, this is usually the one that's more serious to us than the type 2 error. And here's why. All right, let's go back to the criminal trials. We're in the United States. And again, we've assumed that our defendant is innocent until we prove them guilty. So in this case, what's our null hypothesis? Well, that would be that the defendant is not guilty. They're innocent. The alternative is that the defendant is guilty. Now, we always assume the null hypothesis is true unless we've got sufficient evidence, right, beyond a reasonable doubt to reject it. So in hypothesis testing, our data are the evidence, right? If there's enough evidence in our data, we reject the null hypothesis. And if there's not enough, we fail to reject. So in this case, a type 1 error would be like convicting an innocent person, right? The evidence led to a wrong conclusion. And if we made a type 2 error, that would be like setting a guilty person free, right? There's not enough evidence to prove guilt. But because we want a just and fair process, we assume that everyone is innocent, right? Until they're proven guilty beyond a reasonable doubt. And the proof is going to be in that data, this large body of evidence that's going to be presented to suggest whether this person committed a crime or not. Now, if we wanted to say control for the type 2 error, meaning we would never set a guilty person free, we would also end up convicting a lot of innocent people. On the other hand, if we control for the type 1 error and never convict an innocent person, then we end up setting guilty people free as well. So we typically choose the largest alpha that we can tolerate. Let's say alpha equal to 0.05. So what this means is we're willing to mistakenly convict an innocent person 5% of the time in exchange for making the right decision 95% of the time. Now, if we couldn't tolerate that, we could also choose a different level alpha, maybe alpha 0.01. So then we'd mistakenly convict an innocent person 1% of the time, right? And correctly make the decision 99% of the time. We call that alpha our significance level. All right, let's look at the following types of hypotheses. And I want to kind of prep you for where we're going to go with this. 3 ways that we look at hypothesis testing. And first is an upper tail test. So the null hypothesis is that mu equals mu naught, some mean that's assumed under the null, versus the alternative is that our sample comes from a population that has a mean that's greater than the mean under the null. So mu is greater than mu naught. A lower tail test is the opposite of that. Now we're assuming that our sample comes from a mean population that might have a mean that's less than the null. So that's our alternative hypothesis. And then lastly, we can do a 2-tail test. Now we're looking to see if our sample is different from the null, either greater than or less than. Let's start with the upper tail test. Suppose we've got a random sample from a normal distribution, mu and sigma, where sigma is unknown, and we want to do an upper tail test. So the null hypothesis is that mu equals mu naught versus the alternative that mu is greater than mu naught. Now we need first a test statistic. We're going to calculate this from our data. This is our z. So under the null hypothesis, our z is x bar minus the mean under the null divided by sigma over square root of n. And we know that follows a normal distribution. The significance level here is alpha. We can set an alpha equal to, say, 0.05, which would give us a z critical value of 1.645. All right, next we need a rejection region. And so we're going to reject for values of our test statistic z that are greater than or equal to that z alpha, that critical value. And then lastly, we have to make a decision, right? If our test statistic is greater than our critical value, we reject the null hypothesis. Otherwise, we fail to reject. Let's do an example. Here we've sampled a random sample of size 9 from a normal population with an unknown mean, but a standard deviation equal to 1. And here's the values that we get. 2, -3, 6, 1, -2, 4, 0, -1, and 2. Our null hypothesis is that the mean is equal to 0, that this sample comes from a population with a mean of 0. The alternative that we're going to test it against is that the mean is actually greater than 0, that it comes from a population that's greater than 0. So we want to see, is this data strong enough to reject the null hypothesis, to reject that it came from a population with a mean of 0. All right, first we need that test statistic, that z value. That's x bar minus the mean under the null divided by sigma over square root of n. All right, plug in our values, we get 1 minus 0 divided by 1 over the square root of 9, which gives us 3. Here, our significance level, we can use an alpha of 0.05, and we get a critical value, z, alpha of 0.05, of 1.645. Next, we're going to compare our test statistic to our critical value. And we see that 3 is greater than 1.645, so it falls in the rejection region, and we reject the null hypothesis. For a lower tail test, our test statistic z is the same under the null hypothesis, but what changes is the significance level. So we're still going to use an alpha of 0.05, but now we're rejecting for lower values, right? So we're going to reject for a z critical value of minus 1.645. Our rejection region will be if our test statistic falls below that value, and our decision is that we're going to reject the null hypothesis, otherwise fail to reject it. All right, let's do another example. Now we've got a sample of size 16, again from a normal distribution with a standard deviation of 1. And here you see the values that came out of our sample. We want to test the hypothesis that this sample could have come from one with a population mean equal to 0, or the alternative that it might come from a population with a mean less than 0. So first we determine that test statistic, z, x bar minus mu over sigma over square root of n. Notice here when we plug in those values, we get a z test statistic of 0.05. Our significance level is at an alpha of 0.05 as well, and that critical value is negative 1.645. Now, when we compare our test statistic to the critical value, we see that we're actually larger than it. So we actually don't have enough evidence in our data to reject the null hypothesis. So we fail to reject. All right, lastly, I want to show you a two-tailed test. So now we've got a random sample, but we want to test whether we're not equal to the null hypothesis. So in this case, we're going to reject for values that are larger or smaller than the mean that's assumed under the null. Test statistic, exactly the same. Alpha level, also the same, right? We can reject for a positive 1.96 or negative 1.96. Rejection region, now if our critical value is less than negative z alpha over 2 or greater than positive z alpha over 2, we would reject, right? Because our z could either be positive or negative depending on where our data lies. And then for our decision, we're going to reject the null hypothesis if we get a z value that lives in that critical rejection region. Here's a fun example that looks at total cholesterol. So the total cholesterol levels for obese patients have a mean of 200 with a standard deviation of 15. A researcher thinks that drinking 3 glasses of water first thing in the morning is going to have an effect on cholesterol levels. And so we get a sample of 40 patients who've tried the morning water routine, and they have a mean cholesterol level of 182. We want to test the hypothesis that this water actually had an effect. So first we want to state the hypothesis. Here under the null hypothesis, our mean is equal to 200, right? So that's what we're assuming to be true. The alternative is that we're not equal to 200, right? Maybe the water had an effect that caused the cholesterol to go up. Maybe it had an effect that it caused the cholesterol to go down. We don't know. So just the alternative is that the mean is not equal to 200. All right, let's calculate our test statistic. X bar minus 200 divided by the standard deviation, which is 15, over the square root of n, which is 40. Now, when you plug in those values, you get a minus 7.59 for your test statistic. And we're going to compare that to our significance level. But notice now that it's slightly different, right? Our significance level at an alpha of 0.05 means that we're now rejecting if we're above or below, right, in our distribution. So our z critical value is at a 0.05 divided by 2. So z alpha over 2. So that gives us a rejection region at 1.96 that we would compare to our test statistic. Check it out. Our test statistic, if it's greater than 1.96 or less than negative 1.96, we would reject. And negative 7.5 is definitely out in the rejection region. So we reject the null hypothesis in favor of the alternative. So water indeed has an effect on lowering cholesterol. Now, the confidence level and the hypothesis test for the mean is valid provided we've got a large enough sample size, usually approximately 30 or more. But what happens when we've got a small n? We've got a small sample. Well, in that case, we can't really lean on the central limit theorem, right? It's not going to tell us that normality holds when n is small. And here's some of the problems that we run into. First is that our sample standard deviation that we calculate is not as likely to be close to sigma, to that true population standard deviation, right? Because our sample size is small. Now, for our z, we also introduce variability when we calculate that z test statistic. Now, we've already got some variability when we calculate x bar because we're using our sample to estimate x bar. But if we don't know the population standard deviation, we're also using our sample to estimate the sample standard deviation, S. All right, so now that z has error in the numerator and it's also got some extra error in the denominator. And so what results is that the probability distribution of Z no longer looks like a standard normal distribution. It starts to spread out a little more because of that error. And so in this case, we actually have to bring a new family of distributions to the table, the t distribution. All right, notice in this graph, we compare the t distribution to a standard normal. Now you'll see a couple things that are really familiar. The t distribution is bell-shaped. You'll see that the height of it depends on the sample sizes, and this is called our degrees of freedom. Also, the distribution becomes wider for smaller sample sizes, and so this is to try to account for that estimation error. So look what happens. As our degrees of freedom increases, in fact, as it goes to infinity, your t distribution actually converges to the standard normal. So let's formally define our test statistic when we're operating under a t distribution. So in this case, when x bar is the mean of a random sample of size n from a normal distribution with mean mu, then this random variable t equal to x bar minus mu over s over square root of n has a probability distribution called a t distribution with n minus 1 degrees of freedom. And so we write t with a tilde, which means t follows our t distribution with n minus 1 degrees of freedom. Let's do an example. Here we've got a random sample, again from a normal distribution, but notice we don't know sigma. And we want to test whether our alternative, that the mean from the data is greater than the mean from the null hypothesis. In this case, the only difference is our test statistic. Now we're using the t distribution. We're still doing x bar minus the mean under the null, but now we're dividing by the sample standard deviation over the square root of n. We'd compare that to a t distribution at a critical value of alpha and n minus 1, where alpha is our significance level. Now we're going to reject if our test statistic t is greater than or equal to that t alpha critical value. Now, we've covered a lot, and so I want you to see the test statistics together just so you can really understand the difference. Here you see for our hypothesis testing, we said we can either do upper tail test, where we reject for values of our sample that are much larger than the mean under the null. We can do a lower tail test. Now we're going to reject for values of our sample that are much smaller than the mean under the null, or a two-tail test, where we reject for values that are either greater than or less than the null, right? And then our test statistics. For the normal, if we know sigma, we can actually calculate a z statistic, x bar minus the mean under the null divided by sigma over root n. But if we don't know sigma, we have to use the t distribution. Now we're using our sample standard deviation in the denominator. Now, if we've got a large enough sample and we still don't know sigma, that's when we can invoke the power of the central limit theorem. If your sample is about greater than 40 or so, you still don't have to know sigma. You can actually use a standard normal. By then, you've actually converged. Now, another way that we could actually test our hypothesis is by looking at p-values. We perform a hypothesis test. A p-value can actually help us determine the significance of our results. So here's what the p-value does. It actually evaluates how well our sample data supports the arguments in the null hypothesis. How well does our sample data support that the null hypothesis is really true? And so in a way, it's going to measure the compatibility of our data with the null hypothesis, right? How do these two things really get along? And it helps us answer the question, how likely is the effect of seeing our sample if this null hypothesis were really true? Now, high p-values, that tells us our data are really likely if the null hypothesis is true, right? You'd see this data set under this null hypothesis. That's a good thing. When you have low p-values, that says, you know what? Our data isn't really likely under that particular null hypothesis. So let's define it. The p-value is the probability of getting our particular sample, or a sample even more extreme than ours, just by chance when the null hypothesis is true. Okay? So now for a test with a significance level of alpha, we can actually use the following decision rule just looking at p-values. If our p-value is less than or equal to alpha, we can automatically reject the null hypothesis. And if our p-value is greater than alpha, we automatically fail to reject the null. And so a low p-value is suggesting that our sample provides enough evidence that we can reject the null hypothesis. Check out this graph. Right? So it shows the distribution under the null, and you see our observed data point is this test statistic. It's calculated from our sample. Now the shaded red area, this is the probability of seeing our observed sample, or a sample more extreme, by chance, when the null hypothesis is true. Now, the closer our p-values get to the very unlikely zone, the more evidence our data provides to actually reject the null hypothesis. Now, for an upper tail test, here's how we compute the p-value. We're always going to take the probability of our test statistic that we calculate from our sample. And so we're going to calculate the probability that z is greater than or equal to our critical value, given that the null hypothesis is true. So that's that little line there, given the mean is equal to mu naught. For a lower tail test, we're calculating the probability that our test statistic is less than or equal to negative of our critical value. So minus z alpha over 2, assuming the null hypothesis is true. And then for a two-tailed test, we're doing the same thing, but now we've got to add up that area in the tail. So we're going to multiply that probability by 2. So that's the probability that the absolute value of z, because it could be positive or negative, is greater than or equal to the absolute value of our z critical value, z alpha over 2, because it could also be positive or negative, under the assumptions of the null hypothesis. We have to multiply that by 2. Now, if you're doing hypothesis testing with p-values, there are a couple steps that you do first. You're going to state the null and the alternative. You're going to calculate your test statistic. And then you're going to choose a significance level alpha. And then from there, you can use your test statistic to compute your p-value. After you get your p-value, you state your conclusion in terms of the problem. If your p-value is less than or equal to alpha, you reject the null hypothesis. If it's greater than, you fail to reject the null hypothesis. Now, we'll talk more about p-values in the very next lecture, but it's a couple of pitfalls that I don't want you to fall into. A statistical test is not really designed to prove or disprove hypotheses. I mean, it weighs the evidence that you've provided with the data, and then it's going to determine what's warranted. Now, whether we reject the null hypothesis or fail to reject the null hypothesis, well, a significance test is only going to give us evidence for or against the null, although the alternative is what we believe to be true. And even if the null hypothesis is true, remember, there's still a probability that we'd mistakenly reject it. And that's our significance level, alpha.